Pero hay otro, es que hay otro ahora. Hay otro de Rolling, sí. Ya. Ya. Perfecto, chao, gracias. Ok. Vamos a ver esto. Perfecto, ¿vale? Está bien, Rodolfo. Ahí está bien, ¿eh? Sí, sí, oh. Ah, ¿cómo te conectas? Yendo al canal de YouTube. El UI. El UI Systems. Aparece la página del centro, de acá en YouTube. O sea, gracias. Para no parar, sí, no parar.
¿Y se escucha o no?
Microphone is not working. Don't work.
Huh?
Stay close to here.
No, I think it should be fine if you go in here.
Yeah, because the microphone is.
You get this down there? I will go back. Yeah, don't go that far.
Estamos chequeando con los ustedes. El grupo.
Esos son nosotros que.
Está como un minuto desfasado.
Sí, está bien.
Y no se escucha. Porque no hay micrófono.
¿Pero no se escucha?
Ya se escucha ahora.
La censura o ahí. Pero Rolfo nos ha quejado bien de algo, se escuchaba bien.
¿Sí?
Se bien, bien. Claro. Okay, but just in case you stay there.
Here? It's better now?
Can you? Yeah, Rolfo says that there's a little feedback.
I see.
From where? Okay, this is a test. So, I will ask for the delay. Thanks everyone for coming. We are having some technical problems because the broadcast tool that we had before is not working anymore. It was Hangouts Live. They changed the system, so we're trying a new system. So probably it may not be working properly. So I probably asked to the people in linear math than everyone else in the world. Okay, so I'm very happy to have Burak here from Sabanci University. It's the second time he presents this seminar. Last time he visited 2016. And this time he will talk something he is during his postdoc at Seminario with Gerard Conejos and Daniel. Okay. So thanks for coming.
Okay.
The stage is yours.
Okay, thanks, Diego. Thanks for the invitation. I think I need to stay here because the microphone is not working, so I will present from this slides. I hope it's not too inconvenient for you. So, as Diego mentioned, this is a joint work with Daniel and Gerard Conejos. We have done this with Daniel when both of us were at Carnegie Mellon University as postdoctoral fellows. Now Daniel is in Iowa State. So the title of the talk is Computational Aspects of Bayesian Solution Estimators in Stochastic Optimization. So this is quite a different topic than what I usually do. I work on research and non-linear programming problems, optimization methods, etc. So this was kind of a different work for me. So I would also appreciate your feedback. I'm sure some of you might know more than I do in some aspects of this kind of research. So this is the outline, and I will start with the introduction. Okay, so in this talk we are interested in this kind of stochastic programs. We have a function f, which takes arguments x and y. X means the random variables and components in the objective, and y are our decision variables. Now, here the expectation is with respect to x given theta. Here theta is the uncertain parameter, is a parameter of the distribution of x. Okay? Now, if we actually know what theta is, if we know the parameters of the distribution of the random variable x, then this reduces to, let's say, a classical stochastic programming problem. Okay, I'm not saying those are easy to solve anyways, but at least we know some methods to how to solve them. Now, in this talk, we are interested in the case where theta is not known. Okay? And we will call these as parametric stochastic programs. Alright? And the idea is the following. Suppose that we have some data. We have observed some observations from the likely distribution, and potentially we might have some prior on the uncertain parameter theta. In this kind of a situation, how can we obtain good estimators for the optimal solution y star of theta, which we don't know and cannot know because theta is not known? Okay. So there's some related literature on this. For instance, people have looked at parametric stochastic programs before. These are some standard references. One way of handling this kind of problems is through sample average approximation kind of approaches. This has some implications in statistical inference and decision theory as well. And from one aspect, which I will not discuss today, it somehow relates to robust optimization if you use some kind of minimaximality in estimation theory. Okay, so here's our approach. So we know Bayesian statistics from statistics, essentially, and this is an optimization problem. So what we will try to do is combine some of the ideas from statistics and obtain some solution estimators for the stochastic problem I have shown you before. And I will define what we mean by solution estimators and stuff as we go. But to initiate the research, we need to fix two important aspects. The first one is how do we measure the quality of a solution? Okay. So in optimization problems, I guess what makes sense is the objective function difference between the optimal solution and your estimate. Okay? So this we will call this as the linear loss measure, as I will show you in a few minutes. And the second possibility is that if you knew what the optimal solution was, and if you're a solution estimator, you can measure the distance, let's say some norm. So that's the two criteria we will use to measure the quality of the solution estimators. And the second important aspect is how do you compute these solution estimators? And I will talk about two types of solution estimators. The first one, which we will call the separate approach, we will first estimate what theta is from the data, and then use that estimator in the optimization problem. In the second approach, which we will call as the joint approach, we will combine these estimation and optimization procedures at the same time. Okay? And then the question arises, what can we say about the difficulty of obtaining these solution estimators? Is there a trade-off between obtaining the joint estimator rather than a separate estimator and things like that? Okay. Now I want to go through like 2 slides about what Bayesian statistics is and how we will use those ideas in obtaining the solution estimators. So this is a summary slide about Bayesian statistics. So suppose that x is a random variable and its distribution has an unknown parameter theta. So in Bayesian statistics, people usually assume some prior on theta, and they also assume that they have some observations. Okay? From these 2 pieces of information, we can go to the posterior distribution. So once I've seen this data, what's the new distribution of the unknown variable, unknown parameter theta? And they use Bayes' rule. And but in optimization, I guess we are more interested in the distribution of the random variable itself rather than the uncertain parameter. So therefore, it might also make sense to look at something called the posterior predictive, which is exactly the distribution of the random variable having observed the observation x bar. Okay? So this particular distribution will become important as we go along the presentation. So here is the notation. So maybe I can write this down on the board because I will be referring to these distributions quite a lot. So g x given theta is our likelihood function. Little pi of theta is our prior on theta. And we have the capital pi of theta given x bar, which is the posterior distribution. And we also have h of x given x bar, this is the posterior predictive. And just to remind you, x is our random variable, theta is uncertain parameter, and x bar is the data we observed. Okay. Now this is also important from Bayesian statistics. If you have a pair of prior and likelihood functions, which makes the posterior distribution the same as the distribution of the prior, then that family is called a conjugate pair. Okay? And it is working with conjugate pairs is very convenient because you know what the distribution is and you know more stuff as we will see later. Okay. Now, so this is again a slide from statistics. Let's say that our whole aim is to estimate theta. What would be the best approach to do? Now, in statistics, what people use is to define this quadratic loss function. So this is the real value of the theta, and this is your estimator given x bar, which is the data observed. As you can see, this is a random quantity because you don't know theta, and x bar is also random. So, and this is called the loss, and typically what people do is to define something called the risk. Risk is the expectation of the loss with respect to x bar given theta and theta. Therefore, risk actually becomes a number, just a number, okay, like 5. Then once you have a function, you can talk about the best estimate, okay, the estimator which minimizes the risk. And if you obtain such an estimator, then it is called a Bayes estimator. And in the simple case of parameter estimation, this is just the mean of the posterior distribution. So this is also well known from statistics. And here is an example of a nice family of prior and likelihood functions, which are both normal. And if these two information are given, then I can compute the posterior and posterior predictive distributions. Okay. So after this short introduction to Bayesian statistics, let's see how we can apply some of these ideas to optimization, in particular parametric stochastic programs. Again, remember this is the optimization problem we want to solve, and we will assume that theta is unknown, but we will also assume that we have some observations. Okay? For the simplicity of the presentation, I will assume that we have one observation only, but all the ideas can be extended. And the computation results, I will also give you some examples with multiple observations. Okay, so if theta was in fact known, y star of theta would be the true optimal solution, which is not attainable in general because we don't know theta. Therefore, what we will try to do is to obtain a solution estimator, which is given the data, what is my solution. Okay. All right. Again, motivated by the statistics, we will use the risk as our criterion to evaluate the solution quality. And in optimization problems, as I just mentioned, two types of measures are relevant: the difference in the objective function values and the distance between the solutions. Okay. So let me show you some precise definition of these loss functions. So here we are using the linear loss function, which means that this difference between objective function difference of the true optimal solution, which we don't know, and the estimator. Okay, so this I just plugged in these things to the objective, and this is the difference. Okay. As you can see, this is a random quantity. Therefore, what we do is take further expectations to make this a number. Okay, this is something we will call the linear estimation. Okay. Once we define our risk, we can try to obtain the best possible estimator, which will be called the Bayes estimator. Okay, here comes our first main result, which says the following. If we have some likelihood function and prior, then solution estimator should be given by solving this problem or equivalently this problem. And as you can see here, the expectation is taken with respect to the posterior predictive distribution. Okay. So this resembles some of the other results in statistics, but we are applying it to optimization. And we will call this as the joint estimation and optimization procedure, because as you can see, there is no separate procedure to find a good estimator for theta. Okay, so everything is embedded. Okay, but in general, this is not what people use in practice, right? Some people first estimate what theta is, and then use that theta in the optimization procedure. So that's something we will call as the separate approach. And let me show you the main difference. Here is the optimization problem you should have solved with the separate approach. First, you estimate what theta is, and then you bring it to the likelihood function and take expectation with respect to the likelihood. So here is the main difference. Again, to obtain the joint estimator, you need to take the expectation with respect to posterior predictive. To obtain the separates, first you need to find the estimator for theta, and then take the expectation with respect to the likelihood function. Okay. So this is our first measure, linear loss. We also looked at something we call as the quadratic loss, which is the difference between the true optimal solution and our estimator in L2 sense. We have made some assumptions to simplify the notation. In particular, we assume that the true optimal solution is unique with respect to our optimization problem. And then, because again, linear loss is a random number, random variable, we obtain the risk, which is a number, by taking further expectations. Okay. Now, you can ask the following question. Well, there was a separate approach and a joint approach for the linear rows. Does there exist the same procedure? Well, there is, but the thing is that the separate approach is the same under any kind of loss function. Therefore, the separate approach yields the same solution estimator, but the joint approach yields a different estimator, which is the solution to this optimization problem. Let me explain this again. So y star of theta is the true optimal solution, and this expectation is taken with respect to the posterior again, and we measure the distance to our decision. Okay, the optimizer of this will be the joint estimator under quantity loss. Okay, and under some mild assumptions, you can write it as follows. So of course, this is something difficult to obtain in general because you need to know y star of theta explicitly, then take further expectation with respect to the posterior, which can be difficult in general, as I will show examples later. Okay, so that's more about the theory parts of the presentation. Now, in the remaining part of the presentation, I will try to answer some relevant questions that we think we should have answered along this direction. And the first one is the relation between these estimators and possible trade-off between the accuracy and computational complexity. Okay, in particular, I want to answer these two questions. The first one is it possible that the accuracy of the joint estimator is much better than the accuracy of the separate estimator? By construction, of course, joint estimator is better, right? Because that's the way we constructed it. But could it be the case that they have the same computational cost and joint is much better? Therefore, you should definitely use joint estimator. So I will give you some example from portfolio optimization. And we tried so hard with DIIIO to find an example where joint estimation is so difficult to obtain. Maybe you can settle down with separate estimating. Okay? So I will give an example from a geometric programming application. Okay. Now, here's the first application from portfolio optimization. So this is a very simple stylized example from portfolio optimization. Suppose that we have an investor with 1 unit of wealth, and she wants to invest it to N stocks, and the random returns are denoted by the vector x. We will assume that we are given the likelihood function, and the unknown means are given as mu. Later, we will assume some distribution on them. And again, with respect to our Bayesian approach, we will assume that we know a prior mu, and we have some observations drawn from the likelihood function. And let me fix one objective function. Well, objective function, you can perhaps use different ones. We will look at this utility function, which is called U. And if I invested with the portfolio Y and the returns are X, then this is my return and this is my initial wealth. Therefore, this quantity will be my utility. Okay? And we will take the expectation with respect to the likelihood distribution. And in this simple case, we will assume that the feasible region is just a standard simplest. Okay. And as the utility function, we have chosen this exponential form. Okay, let's see the consequences. First of all, let me show you how to obtain these estimators in general. To obtain the separate estimator, again, if you recall, first we need to compute the base estimator for the uncertain parameter mu, and then plug that in to the likelihood function and take it. Okay, and then solve this optimization problem. In the joint approach, the expectations should be taken with respect to the posterior period. Okay. Now we will make some assumptions on distribution so that we can numerically solve these problems and obtain some intuition. We will assume that everything is normal, multivariate normal, and I will not show you the derivation, but under this utility function, and if you use some properties of the exponential functions, these estimation problems reduces to these two quality problems, which resembles somehow Markov's model. Okay? And the difference is that the covariance functions are different. The covariance matrices are different. Okay? So this is for the separate approach, and this is for the joint approach. So typically, joint approach is somehow more conservative in some circumstances. Okay, so let me show you some numbers. We use a real data set from Standard & Poor's 500 index, spanning 30 years. And we looked at just 11 sectors instead of working with each stock separately. And to obtain a prior information, we use something called Black-Littman approach, which I will not explain now. But if you are familiar with that, there are some parameters of the Black-Littman approach, which we also fixed. If you are not familiar, just think of it as a method to obtain prior distributions. Okay. And recall that we had 360 months. We use 180 of them in the estimation and use that estimation to make a decision for a portfolio. And we evaluate the performance of the portfolio in the next time periods, which we have not seen, so that we can measure how good our estimators are. Okay? So this is the exact procedure, but I don't want to go through the details that much, but if you're interested, I can explain more. Rather, I want to show you this picture. Okay, I hope you can see everything clearly here. Now, our aim is the following. We want to understand the difference between the joint and separate approaches, but there are some parameters we have to fix. Therefore, we tried with many different parameters, and
lambda was the coefficient exponential?
Yes. Yes. Lambda was risk aversion, so large lambda means high risk aversion. Yes. And tau is how comfortable with you to assume that the prior is weak or strong. Okay? So, which means that small tau means strong prior. So you believe in the prior more than you believe in the data. Yes. Okay, and here in this picture there are three charts. In the first one, I'm looking at the average return, which I want to be large, obviously. And the second and third one somehow measure the risk, which I want to be as small as possible. And in this chart, for instance, the ones with dots, large dots, represents the separate approach, which, as you can see, are dominated by the joint approaches, which are given by statements. Okay, and you can say the same thing for the risk. Risk of the joint approaches are lower in terms of the standard deviation measure and clinician averages. Okay, so this is an expected result somehow because joints should be better than separate. And I think another interesting observation is that the performance of the separate approach really depends on how you fix this tau, which is your confidence to the prior, and lambda. Lambda was your risk aversion. Whereas for the joints, it seems that they are more robust to these parameter selections. Okay, again, as I said, maybe this expected result. So let me show you a slightly different intuition. And in this case, we will look at stochastic geometric programs. So let me explain you what a geometric program is. In a geometric program, you have expressions of this kind, where you have exponential functions and sometimes log functions after transformation. So I wasn't aware of this, but this has many applications in engineering, apparently in chemical engineering and chip design and electronics, etc. Okay, but for our purposes, this function is somehow very nice because you are taking the exponential of a random variable, which brings us the idea of moment-generating functions. Okay. Therefore, if you take this expectation, actually, and if you work it out, it becomes the moment-generating functions of the random variables, and then you multiply them, assuming independence, you can work it out. Okay. Now the question reduces to the following: are there distributions for which moment-generating function of the likelihood is nice, but the posterior predictive is not so nice? Okay, in terms of computations. Well, I think we have found one family which satisfies these conditions, and okay, this is the general results. Maybe I can just briefly mention. For the separate approach, we need to take the moment-generating function of the likelihood. For the joint approach, the posterior. Okay. So it turns out that if I choose a likelihood of exponential function and a prior of gamma, then because the moment-generating function of exponential is nice, I know it's equals 1. But the posterior predictive of this distribution pair is something called Lomax, which I didn't know before, and it doesn't have a closed form expression, and it is very difficult to estimate it further. Okay, so therefore this gives some kind of a trade-off between the joint and separate approaches. In the separate approach, you can actually solve some problems, whereas in the joint approach, well, there are some difficulties. I will show you some numbers now. I think I can safely skip the slides by just saying that the separate approach, to obtain separate estimator, you need to solve a complex program. To solve the joint approach, because we don't have a closed form solution, the only method you can use seems to be some kind of standard version. Okay. And here are some numbers. So in the first column, I'm reporting the separate approach, the objective function value of 5 instances, and the solution time to obtain them. Okay. Now, and here we have the sampling approach for the joint methods with different number of samples. And one observation you can make is that joint approach does not seem to be converging very fast. And I think with my laptop, I wasn't able to solve this 100,000 sample problem very easily. So because of memory issues and everything. Therefore, as you can see, joint approach has some convergence issues, whereas separate approach, you can really solve it very fast. Of course, unfortunately, this doesn't tell you the solution quality of the separate and joint approaches necessarily, because you couldn't solve the joint approach, really, you don't know whether you obtained the optimal solution or not. Okay? Therefore, comparing the objective function values might be misleading, so that's what I mean. Okay.
In this case, the objective value is just the objective value of the sample that you obtain. You're doing a sort of posterior sensitivity analysis.
No, yeah, you're right.
Out of sample.
No, we haven't done that. Yes, sure. Okay. Now, in the next section, we will try to answer some similar questions from a different point of view. So you might ask the following question: now, have people been doing everything wrong to this point? Why are we not using the joint approach instead of separate, etc. Well, I will show you when they are the same, which might be comforting, and when they are not the same. Okay? Again, I will show some sufficient conditions under which these two approaches are the same, and when they are different, I will again show you, at least give you some idea about whether they can be arbitrarily different from each other, which is possible. Okay. So here is another here's the results we obtained. So if we look at the linear laws, when is the case that the separate and joint estimators are the same? So it turns out that if your objective function is linear in terms of theta, then you are fine. In the sense that the joint estimator and separate estimator are the same. Which means, I will show you some examples, but this may be the case in many applications. If your objective function is linear in terms of uncertain parameter theta, then you are fine. You don't need to worry about these joint and separate approaches, which means that to make a difference, the objective function should be somehow non-linear. Okay? Okay. So that's why I'm always looking at this kind of, let's say, weird applications like geometry programming. Okay? Okay, this is for the linear laws. How about quadratic laws? Well, for quadratic laws, it's a little bit more difficult because you need to first find y star of theta, which is the true solution in terms of theta. And if it turns out to be multilinear in theta, then again, there is no difference between the joint and the separate approaches. Okay, I think I have some examples illustrating this. So let's look at a very simple Markowitz type of optimization problem with no explicit constraints. And here in the first example, our uncertain parameter is mu. And as you can see, this is a quadratic program, and you can obtain the optimal solution explicitly, very easily. And again, as you can see, the objective function is linear in mu. Therefore, the joints under linear and separate should be the same by our result. And again, this is a very particular case where you can actually solve for the optimal solution, which turns out to be linear in mu. Therefore, joint under quadratic is equal to the separate. So all of them are the same. You are good. Okay. Now I will tweak this problem a little bit and move the risk parts to the constraint. What else? Well, in this case, we can again solve for the optimal solution explicitly. And again, I'm not changing the objective function. Therefore, joint under linear and separate are the same. It turns out this is the answer. But joint under quadratic is quite messy. As I mentioned before, first you need to solve for each mu, and then take the expectation with respect to the posterior distribution. And as you can see, this is already nonlinear. You need to take an expectation, which is quite difficult. So this is a case where these two are possibly different. Okay, and here is another example. In this example, we are back to the first optimization problem, but now we assume that lambda is uncertain. Lambda is our risk aversion. Maybe you don't know what lambda is. In this case, you can still solve for the optimal solution, which is linear in mu. Therefore, separate and joint under quadratic are the same, but the linear loss gives you something else. Okay, and if you work enough, you can find examples where all the things are different. Okay. And this is the answer to the second question in this section. Can they be arbitrarily different? Can these estimators be arbitrarily different? Well, it is possible. For instance, if your optimization problem looks like this, and you have an uncertain parameter mu I, and the feasible region is a simplex again, then you can find numbers, which I don't show here, in such a way that the separate and joint estimators lead to two different extreme points of the syntax. Therefore, this is an indication that it's can be arbitrary bad because they are totally different. Right? And on the quadratic laws, we have found an example with a linear objective and a quadratic constraint or a ball constraint, in which the separate estimator gives you a point on the boundary where the joint estimator is approaching to the origin. So the difference is, in some sense, as large as possible of the factors. Again, you need to fix some certain numbers to obtain this.
When you take mu square, we could call that mu. The first problem, because it's quadratic in mu.
Yes.
So mu square is a different uncertain parameter.
Yes.
We call mu just.
But the distribution will be different. The distribution of the new parameter will be different.
So it's about the distribution of the mu. So this is for normal distribution of the mu.
I think I don't remember the distribution we had, but it could be normal. I can check it later. Yes, but you are right. It's really about the distribution that you fix. Okay. And the final part of the presentation is about piecewise linear structures. As I mentioned, you need some nonlinearity, and piecewise linears are the easiest nonlinearity that you can think about. So let's see. So in this part, we will try to answer these two questions again. Are there some special cases in which you can find the upper bound on the risk? So you are sure about how much you are losing by using the separate approach. Well, as the title gives away, we will look at the piecewise linear form. And I will also look at some practical application in which piecewise linear functions appear, and there's a large performance gap, which is something maybe predicted. And here we will give an example from neural networks. A very stylized example from neural networks. Okay, I'm sure everyone in the audience are very familiar with piecewise linear functions, and they're used in operations research kind of applications. And here are some examples like inventory control, pricing, logistics, and machine learning. In particular, we will look at something called the rectifier. I will show you what it is. Again, more motivation. The first example is a very simple single station assembly problem. I don't need to go through everything, but eventually your object function looks like this, which is a piecewise linear function. And the second example is kind of a one-dimensional stochastic median problem. So think of a line, and you want to, let's say, locate an emergency center or something like that. And you don't know where the mat is exactly, but you have some observations, and using these observations, you want to locate this facility. And because you are in one-dimensional space, it only makes sense to use the absolute value, and which is obviously a piecewise linear function. And in this case, because you have many locations, many customers, potentially, you are summing them. Therefore, this is an example with piecewise, sum of piecewise linear functions, which are harder to analyze. Okay, so if you look at the paper, this section becomes so tedious very quickly, so I will just give you the simplest example where I can explain in a few minutes. Okay, so here is the first example we looked at. Only one breakpoint, univariate, continuous objective, very nice, and Newsman, there is an example of this. Okay? And in this particular case, we can actually obtain all these estimators in some sort of form. I'm not saying they're always easy to obtain, but at least we have a formula. I think now you have some idea about how to obtain the separates. You look at the likelihood function fixed to a certain point of the base estimator of uncertain parameter. For the joint under linear, you look at posterior predictive. Again, for the joints under quadratic laws, you need to first solve the problem and then take the expectation. So for some certain distributions, these are easy to obtain. For some of them, you need some additional work. Okay, I will give you a table. Okay. Again, as I said, this is the nicest example we were able to find out. Suppose that the likelihood is normal, prior is also normal, and we have just a single observation. What are the estimators? Well, it turns out that these are the estimators. Separate and joint under quadratic become equal to each other, and this is the formula essentially, and this is joint under linear. So the difference is very tiny. As you can see here, we have theta, here we have theta times 2 minus rho, where rho is defined as 1. Okay? So for instance, they are equal if rho is 1. Rho is equal to 1 means that delta is 0. And delta is 0 means that you are certain about your prior, which sort of makes sense. Okay. So what we were able to compute is the risk difference between the separate approach and the joint approach. Of course, this is a non-negative number, so we are trying to upper bound that. And after some straightforward algebra, we obtain this expression where this delta star is a constant. But as you can see here, it also depends on delta. So if, in fact, delta was 0, then they are the same, and this is just under justification. So really, delta becomes important in measuring the difference between these two estimators. Okay, and we go ahead and looked at different likelihoods and prior pairs, and I only showed you the first row of this matrix, and these are the efforts that you have to pay to obtain these estimators. For instance, if you have a likelihood exponential and prior gamma, then you can obtain the separate and joint under quadratic area cross form. This is a very nice example. So you might question, well, does this make sense to assume these kind of distributions? Well, in the literature, I've found a few examples, a few papers. In fact, people assume this kind of exponential gamma pairs for the demand distribution for some certain application, which I don't remember right now, but apparently they exist. And we also wanted to look at the discrete distribution, so that's why we looked at geometric and beta, and yeah, there are some efforts you have to pay to obtain these estimators. And I think for most of these cases, we also obtained similar upper bounds on the risk, which I will not bore you with them. So they are very messy, complicated, tedious expressions. Even worse is if you look at some of these isomorphic functions, like the stochastic median example. So again, even more tedious. So I will skip that. And instead, finish the presentation with a different example, which is this deep neural networks. Again, very stylized, maybe not practically important, but from our perspective, it shows the value. Okay, so suppose that we have n features, and these features are given by x1 up to xn. And you have an output function which takes these random variables, multiplies them with some true but unknown weights to us, and computes this where epsilon is a random error, and then we take the maximum between 0 and this number. So this is called a rectifier, and this we use in deep neural networks very often. So think about the following. For instance, you can observe some x's, and you can observe some O's, and then your aim is to try to find the W's. Okay, like a regression type of general learning problem. Okay, we will represent this with a single layer neural network like this, and we will try to find out the y variables. And to determine these y variables, we will measure our distance to the, this is our prediction, this is the observed value, and these are random because O and X are random. Therefore, you take expectation with respect to S. Okay, so we will try to solve this problem. This is the stochastic program we want to solve. Okay, and as the title says, the slopes are random in this case because we are multiplying x and y. Okay, in the previous example, the intercept was the breakpoint was random, which is related to the intercept. Okay, so again, this is how you would obtain the separate estimator. You first estimate mu and plug that in, solve with respect to the likelihood. And for the joint, you directly use the posterior predictive. Okay. Now, as you might guess, almost independent of what your distributions are, these problems are not so easy to solve directly in closed form. Therefore, we had to use some sampling. So here we use some sampling. And here is the sampled problem that you have to solve. And I think I have the exact setting. So again, we assume everything is to be normal, and we assume that we have multiple observations. And these two information already give you how to obtain posterior and predictive. And here is the setting, the exact numbers. And you also have to set an error term because we will generate this data synthetically. And maybe relevance to mixed integer programmers in the audience, you have to assume some upper bound for this kind of expressions to linearize everything. So I think by itself it's kind of an interesting MIP problem. But we haven't looked at this very deeply. Okay. As you can see, there is a sigma bar, which I didn't specify. I have different experiments for different values of sigma bar in the next slides.
Sorry? What is the bound?
Okay. So let me go back. So I need the bound to upper bound this quantity because I want to linearize this expression. And because this is a maximum, I want it to be equal to that, right?
Yeah.
To be equal, I need an upper bound. And we need to define binary variables to take care of that. Which is not so nice, I have to admit, but we had to assume some number. Okay, so here are the results. I think here we had 1,000 samples to solve these sample approximation problems. And these are the test area results. So we train them and then use them in a different new batch of samples and compute the test errors. So these are, let's say, reliable numbers in some sense. Okay, so here I have different results for sigma bar, and remember sigma bar was the upper bound on the sigma, and sigma is the variance related to the variance of the likelihood function. So one thing you can observe is that separate is significantly worse than joint in general.
What are the numbers?
Sorry?
What are the numbers?
The numbers are the test area results.
Okay.
So I think I have 1,000 samples here each, and 1,000 new samples. I used my prediction model to find the difference between the prediction and the correct value, and then take the average over the 1,000 samples and repeat this 10 times and report them. Especially if you increase the sigma bar, you can see some quite bad numbers, but joint is pretty much very consistent. Okay, so that was the conclusion here. And so let me conclude with 2 more slides. So in this talk, we looked at optimization problems which involve uncertain parameters, and in the presence of data, how we can solve them using some ideas from statistics. We use 2 different risk measures and 2 different approaches, separate and joint approach, and compare and contrast them whenever possible. And we also looked at further into some nonlinear stochastic programs like piecewise linear and geometric. And maybe some future research directions. So far, we only assume that uncertainty is in the objective function. How can you incorporate uncertainty in the constraints? So this seems unknown to me. How to do it is not so clear. Maybe more interesting, another interesting application is if you see data in an online or dynamic setting, how can you obtain these kind of estimators? Can you say anything for the joint approach if you have non-conjugate pairs? So working with conjugate pairs is very nice because you know the posterior mean and things like that in closed form. But for non-conjugate pairs, you don't know. There is no form. Okay? So in general, people use some sampling to estimate them. So it's a difficult case. And I know some applications where people actually use separate instead of joint, and in their applications, the functions are really nonlinear. So therefore, it might make a difference to use joint instead of the separate approach. And here are some examples that I know. Okay. So that's the end of the presentation. Thanks a lot for listening, and it's very good to be at Seminario. Thank you.
Questions for Burak?
Thanks again, Burak.
Just a comment, because you mentioned that the joint approach may face difficulties because of sound.
Yeah, that's true.
Then you sort to sample our approximation, but why didn't you think of doing stochastic approximation? Just using one sample. Did you try that, or?
Actually, we haven't thought of that. Yeah, I mean, yes, that's a good suggestion.
That's a pretty obvious question. Maybe you could add it to the introduce.
Okay, that's a good idea. Yeah. No, it's
It's always the same idea.
Yeah, you're right. Okay. Thank you.
What can we say?
Building tank? No, perfect. Tem algum favorito?
Good for?
Good for.
So ways of you implement all this? Did you use